All right, so what's the net force? That's a valid question, I'm going to say. The reason it's a valid question is because in real life, we got multiple forces acting on, right? It's not just a single force, it's multiple forces acting at all times. Okay, so what do we have here? We got the weight acting on this guy. There's a push here, there's a retarding force. This is the force which is there to retard the motion of this mass. Okay, so we got these multiple forces acting at all times. If that's the case, which force is responsible for the acceleration?
Chopping down a tree clean through by hand is a thing of the past. Pulling down a 30-foot evergreen with a tractor makes sense. But not with a 10-foot rope. Chopping down a tree clean through by hand is a thing of the past.
The tree got two forces acting on it along the horizontal direction. There's one force pulling it to the left. There's a second force pulling it to the right, right? So the rope is pulling it to the left. The roots are pulling it to the right. As a result, the tree topples over. So when you have two forces acting in opposite directions, what is the net force? So imagine that you got this object, the mass, and there are two forces acting on it. 21 pounds to the right, 20 pounds to the left. So what's the net force? Okay, so let me give you the definition of the net force. Definition of the net force is the sum total of all the forces acting on this mass. Definition is the sum total of all forces acting on this mass. Got it? So which means that you have to sum up the forces. Now, when you're summing up these forces, what do you get? You got 25 pounds to the right, you got 20 pounds to the left. You're thinking, oh, does that mean it's 45 pounds? Think about it, guys. Really, is that 45 pounds? So think about it from your real life experiences, experiential perspective. If somebody's pulling on in this direction with the 25 pounds of force, somebody's pulling in the opposite direction with 20 pounds of force, what's the net force? You know it's going to be 5, right? When you sum them up, you end up getting 5. Why? Because the direction matters. Because the direction matters. All of a sudden, you realize that the direction matters in a sense that, hey, which means that force to the right is going to be positive or negative, force to the left is going to be positive or negative, right? So the direction matters in terms of how you add these things up. All right, so forces to the right, we'll take them to be positive. Forces to the left is going to be negative. Now we can just sum up the forces easily. All right, so net force means summation of all the forces, in this case, along the x direction. It's a summation sign. What that means is we're just summing up the forces along the x direction. You can sum up the forces along the y direction. You can sum up the forces along the x direction. So the net force is the summation of all forces along the x direction, which is going to be responsible for that acceleration along the x direction. Got it? So the acceleration along the x direction is going to be caused by the net force along the x direction. So the acceleration is caused by the net force. Net force is the summation of all the forces. All right, so now we're summing up the forces. F1 is to the right, so it's going to be positive. F2 is to the left, so it's going to be negative. So just sum them up, it's going to give us 5 pounds. All right, so that's how it's going to be done.
The dummy contorts and stretches from the immense force. In only seconds, its arm is wrenched off by one of the aircraft, while the other plane drags the broken torso down the runway. Stanley knows the same thing could happen to him, but he's determined not to back out.
We'll make it.
We're gonna make it.
I know.
Come on, Dad.
It's time. The pilots gun the engines. The ropes pull tight as the two Cessnas try to take off at the same time, at the same speed, in opposite directions. Their tachometers have already risen to 1,500 revolutions per minute. Remember, the goal is 2,400. Stanley braces against the tremendous force. Now, at 2,000 RPMs, nearly enough to take off. He grimaces as he fights to hold his ground. Barbara watches, terrified and helpless.
All right, so here's a question for you. What's the net force acting on him right at this moment? Okay, so what's the net force acting on him right now?
0.
Okay, it is 0. Give yourself 5 pounds. So here's a question for you. How do you know that it's going to be 0?
He's not moving one way or the other. He's
okay. So that's not a bad answer either. So I'm looking for. Okay, so one of the things that we need to figure out is, yeah, he's not moving, but what do you mean that the net force acting on it is 0? Okay, the reason why I'm asking that question, let me give you 5 points because you're actually verbalizing something that everybody's actually thinking. It's 0. And that's the way you guys are thinking about it, because it's not moving, right? That's a really good way of saying it, because he is not moving. That's the reason why the net force is 0. That's the way you guys are thinking.
Is it like constant? Like the force is constant because like the two objects are like opposites?
Okay, think of it, you keep yourself out. Think of it this way. Number one, he's got tremendous amount of forces acting on, right? Okay, I mean, I could just take his place. I could just take his place and I will lose my arms. So what do you mean that the net force is acting on him is 0? One way of saying it is, well, he's not moving, but that's not what I'm looking for. What is the evidence of a force? Evidence of a force is acceleration, right? So the evidence of a force is acceleration. It's the accelerator. No, if he's not accelerating, there's no net force is zero. It doesn't mean that there are no forces acting on him. There are forces acting on him, except the net force is zero. When you sum them up, they add up to zero. That's what it means. How do you know? He's not accelerating. He's not accelerating. Okay, always go back to the definitions, guys. Always go back to the definitions. How do you know that the net force is zero? Well, because he's not accelerating. There you go. That's how you know. Okay, is that making sense? Now move forward.
The tachometers now read 2200. More than enough power to take off. Stanley has only 200 RPMs to go. Then suddenly, he's pulled off balance.
Okay, so is there a net force acting on him now? The answer to that question is yes, right? How do you know? Because now he's accelerating. How do you know that he's accelerating? Because he went from zero to something else. That's it. He could be moving, but if he's moving at a constant speed, the net force is still zero. Okay, so what do we learn from this? He's accelerating, so there's a net force. And this is kind of crucial. This one is important because if the force applied by this airplane is slightly larger than the force applied by the other one, he can lose his balance. He can lose his arm. So this sort of stuff is actually dangerous. All right, so it's crucial that both airplanes apply the same force. If the forces are the same, then the net force is zero. It's fine.
It looks like he's being overpowered, but somehow he summons all his physical and mental strength to stop the two planes from tearing him apart. Both engines are now revving at a fierce 2300 RPMs, more than enough for them to be climbing into the sky. And finally, 2400. Stanley has done it.
All right, so pick out the best answer and put it in the chat. Okay, moves in the direction of a force at a constant. If there's a constant net force acting, if there's a constant net force acting on a mass, yeah, guys, you got it. So there would be a constant acceleration. So the constant net force is going to give you a constant acceleration. Constant net force is going to give you a constant acceleration. All right, so give yourself 5 points for that one. God, this is so complicated. Okay, so where we at? Okay, so we got two equal horizontal forces acting on a box. Okay, so we got two forces. A is not the right answer because it's going to accelerate in the direction of the larger of the two forces. These forces have the same magnitude, so that's not a reasonable answer. Moves in the direction of the net force at a constant speed. If there's a net force, you will get to accelerate, so that's not correct. Moves in the opposite direction of the net force at a constant speed. That's once again the same reason. It's not correct. Moves in the opposite direction of the net force at a constant. That's objects accelerate in the direction of the force. So E is the best answer for this one, right? So what it means, it does not accelerate because the net force acting on it is zero. That's the only reasonable explanation that we could come up with. Okay. Okay, so we did a lecture review already. Okay, so what's the net force? Okay, so the net force is the sum total of all forces acting on a system, right? So the direction is going to matter. So the right positive to the left is going to be negative. F1 is to the right, so it's going to be positive. F2 is to the left, so it's going to be negative. So the net force is responsible for the acceleration. So that's the only that we have done so far. Okay, so the weight is the gravitational force acting on an object. So the measure of gravity becomes your own weight. So the force of gravity acting on a mass is known as its weight. Okay, so you got the Newton sample. When you let it go, it's going to accelerate. It's accelerating because there's a force acting on it, because force is what causes acceleration, right? All right, so experience the force in the downward direction. All right, so when it's accelerating, it's going to accelerate at a constant rate. So it's going to be roughly about 10 meters per second squared. All right, so acceleration becomes g. This is the same mass, so this force becomes your weight. So the force of gravity is the same as your weight. So W represents weight, M is mass, and G is roughly about 10 meters per second squared. So weight is the amount of force acting on this mass. The amount of force of gravity acting on this mass becomes its own weight. It becomes the weight of an object. All right, so what happens to the weight when an object stops falling? What happens to that particular weight when the object stops falling? All right, so how much do you guys weigh? All right, so you know how much you weigh. How do you know how much you weigh? Because you weigh yourself on a scale. And then presumably that information is also available on your driver's license, right? All right, so everybody weighs something. Having said that, now this thing is going to weigh something while it's accelerating, right? All right, so the acceleration is roughly about 10 meters per second squared. All right, so W is mg, so g is roughly about 10 meters per second squared. As it's falling, it's accelerating. It's accelerating at a constant rate. But notice that when I catch it, it stops accelerating, right? So when I catch it, it stops accelerating. Got it? So what's the acceleration right now? It's 0, right? While it's falling, it's 10. When it stops accelerating, it's 0. So it no longer accelerates. Right now, it's not accelerating. So what's the acceleration? 0. 0. All right, so how much does it weigh given the fact that it stops accelerating? Think about it, guys. When it's falling, mg, mass times your acceleration, is going to give you a weight. But as soon as it stops falling, acceleration is 0. So what is 0 times 1? 0. 0 times 100 is still 0. 0 times a million is still 0. 0 times a building is 0. 0 times a Fort Tambo is still 0. 0 times cannon is still 0, right? 0 times mass is going to be 0. Does this mean that this thing is weightless when it stops accelerating? Okay, so most of you guys are at this point either standing on a chair or standing up, right? What's your acceleration right now? It's 0. So 0 acceleration times your mass, what do you get? You end up getting 0. Does this mean that you're not falling? You're weightless? You know the answer to that question, right? The answer to that question is no, because despite the fact that this thing is not accelerating right now, I'm holding onto it. As I'm holding onto it, I can feel its weight. All right, so this thing is not accelerating. I can feel its weight in my hand. There's no acceleration here, but I can feel its weight. So if that's the case, when the acceleration is 0, why is it that the weight is not 0 according to this formula? There's something wrong with the formula. Notice that this thing still got weight, except it stopped accelerating. The reason why it stopped accelerating because it is on a surface right now. So it's applying a force on the surface with its weight. This becomes the action force. In turn, the surface will apply the same amount of force back on it. This is the reaction force. And this force is going to be 90 degrees to the surface. That's the reason why it's known as the normal force. Normal doesn't mean normal versus abnormal. It just means that it's a force which is 90 degrees to the surface, and it's a surface force. All right, so this is known as the normal force. Action force is acting on the surface. Reaction force is acting back on the apple. So that's the normal force. Normal means it's a force which is 90 degrees to the surface. I don't know why we call it the normal force instead of the surface force, but it's the same. All right, so it's a reaction force against any force applied to a surface. That's what it means. All right, so normal force is a reaction force to any force applied to the surface. All right, otherwise, this is known as the apparent weight because this is the reading that you get from a scale. This is the scale reading. So instead of the actual weight, we call it the apparent weight because of that. Apparent weight. Apparently, this is the weight that we got. All right, so now sum up the forces on the y direction. So there's no acceleration on the y direction, right? Because this object stops falling. So the net force on the y direction is going to end up to 0. Still got weight. Normal force is in the opposite direction. So let's sum up the force on the y direction. N is up, so it's going to be positive. W is down, it's going to be negative. N is up, positive. W is down, it's going to be negative. Acceleration is going to be 0. So which means that the M minus W is going to be 0, which means that N is going to equal to W. W is your actual weight, and N is your apparent weight. Okay, so they may or may not be the same. W is the actual force of gravity. This is the effect of gravity on your mass. N is the reading that you get from a scale within this context. It's the normal force, the apparent weight. They will mean the same thing. All right, so W represents your weight. This is the amount of gravitational pull that you experience.
Lifting huge amounts of steel has macho man appeal. To compete, it takes massive muscles, the strength of Hercules, and guts of steel. But sometimes it's the tiniest mishap that brings these tough guys to their knees. Weightlifter Stephen Therian knows better than anyone the power it takes in his sport. He's a world record holder in the hand and thigh lift. This day he's attempting 1,500 pounds, 6 times his body weight. He clears it easily. But ever the competitor, Stephen adds some more weight. A measly 10 pounds. A clean lift will now put him in the record books. Unfortunately, he'll break something other than the record. It's a gruesome sight as
Okay, so just because something is not accelerating does not mean that there's no net force acting on it, right? Just because something is not accelerating does not mean that this thing is weightless. It's got tremendous amount
his
of weight
leg crumbles.
to an extent that this guy's leg literally snaps.
The weight is too much for his body to bear. The fibula and tibia bones in his right leg snap like twigs.
That was disgusting. So let's move forward. All right, so there's no acceleration, but there's weight. Okay, so the weight is the pull of gravity. If you can just measure the pull of gravity, the measured pull of gravitational force becomes your own weight. The reason why the object stops accelerating because the net force acting on it is 0. The net force is 0 because there's a reaction force acting on this object. So this object is on a surface. In this case, we got a book. It's got weight. And so the gravity pulls it in the downward direction. So it's applying a force on the surface. In turn, the surface applies the same force back on it in the opposite direction. That's the reaction force. Action and reaction forces are the same. They're in opposite directions. All right, so the net force acting on this block is going to be 0 as a result. So it's called the apparent weight in this case. So weight is the gravitational force acting on this object. Okay, okay, we already discussed that, so let's move forward. Apparent weight is also known as, the normal force is also known as your apparent weight. This is the reading that you get from a scale. For whatever reason, if the downward force is larger than the upward force, the normal force, obviously the surface is going to break. Or you can smash or crank something.
Make room for shoes. The world's biggest shoe store is here.
All right, so the next question is apparent weight and the actual weight. Apparent weight is your scale reading. Actual weight is the gravitational acceleration due to the pull of gravity, right? They don't necessarily have to be the same. You can follow a scale. You can follow a scale. All right, for whatever reason, if you don't like your scale rating, you can adjust the scale. So your apparent weight does not need to be the same as your actual weight. Now imagine that you're 400 pounds. You got a problem with that. You want to diet. Your daily goal is like 10 pounds a day, and you're not going to eat anything. You're not going to drink any water until you reach that goal, right? That's what you're shooting for. Not a realistic goal, but that's a desperate goal. 400 pounds, 400 pounds. So what do? You diet, you're dieting for a couple hours. You're not drinking water. You're not doing anything. You're not eating anything. You're feeling really hungry. So you go into the bathroom, check to see if you lost 10 pounds, right? Because you have given yourself 2 hours. You get on the scale. You look down. What do you see? It's still going to be 400 pounds, right? In 2 hours is not going to make any difference. But you want to hang on to that goal. You don't want to leave the bathroom until you lose 10 pounds, but you're feeling so hungry that this needs to get done within the next 30 seconds or so. So how do you lose 10 pounds within 30 seconds? How do you lose 10 pounds within 30 seconds? All right, guys, don't chop off body parts. Okay, that's not how it's going to be done. You know you can fool the scale. How? It's easy. How do you fool a scale?
Oh, 225. That means I lost weight.
Homer, you're on the towel rack.
So if you shift some of that weight on a towel rack or put your arm on a countertop, you know you will weigh less, right? That's how you do. The only thing you have to do is just fool the scale for a few seconds. As soon as the scale is fooled, you lost 10 pounds. Go easy.
Woo! 4 more pounds and my dream comes true. Working at home.
All right, so scale is going to be sensitive to what happens on top of it as well. You can shift your weight. You can make yourself heavier. You can make yourself lighter. On top of that, the scale is probably going to be sensitive to your acceleration. All right, so pick out the best answer, put it in the chat. Whatever. Okay, so the normal force is reaction force that comes into existence when there's an action force acting on a surface. Normal force is a result. A is the best answer. All right, so most of you guys missed it. It doesn't have to equal to the weight of an object. It can be bigger than the weight. It can be smaller than the weight. Just like the person standing on top of the scale, if that person shifts her weight, his or her weight onto a different surface, then the person is going to end up weighing less or more. All right, so A is the best answer for them. Also, your apparent weight, the reading that you get from a scale, will be sensitive. So your apparent weight is going to be sensitive to what goes on in terms of acceleration. Okay, case in point, this one is a high school physics experiment. All right, I don't think we have scales at school. All right, this is a little experiment that you probably have to do yourselves. I'm going to turn this into a take-home experiment in the future. It's a cute little experiment. So you're inside the scale. You're inside the scale. What am I saying? It's Monday. All right, so you're inside an elevator. All right, so the elevator starts to move from rest in the downward direction, right? So it starts to accelerate in the downward direction. Do you feel heavier, lighter, about the same? You know the answer, right? Okay, most of you guys are motion sensitive enough to know that you will feel lighter. So as soon as the elevator starts moving in the downward direction, as soon as it starts to accelerate in the downward direction, you will feel lighter. You will feel lighter, yeah? Got it? So the question is why? All right, is this just a feeling that you get, or is this really what happens when you find yourself in an elevator moving in the downward direction, accelerating in the downward direction? All right, so the only way to find that is just get a scale and stand on top of it. Okay, so when you feel lighter when the elevator starts to go down, is it because it's just a feeling that you have, but is that just a feeling that you get, or is this really what happens if you're standing on a scale? Take a look at this guy. All right, so this is done by one of the Chicago students, art students. This guy weighs 240 pounds. He's in a high rise. I'm not sure why he's not wearing shoes, socks. And as soon as the elevator starts to move in the downward direction, notice that he becomes lighter according to the scale. All right, so the reading goes down. All right, so which means that when the elevator starts to accelerate in the downward direction, you literally feel lighter according to the scale. Okay, not only do you feel lighter, but you also become lighter according to the scale. So the question is why? All right, so but when the elevator starts to move at a constant speed, the elevator is going to accelerate to a certain speed, and then it's going to keep moving at that speed downward. Do you feel lighter, heavier, or about the same? Okay, you know the answer, right? You will feel the same. So this guy is feeling the same. He's moving at 200. He's moving at constant speed. His actual weight is 240, so it's still. Now the elevator is, while it's going down, it's slowing down, right? So when the elevator is going down and slowing down, you feel heavier, lighter, about the same. Now you know the answer, so you will feel heavy. All right, so it's going down, it's slowing down, and you are feeling heavy. All right, so you got a bunch of facts, so let's just focus on the facts just for now. When there's no acceleration, no change in weight. Acceleration is in the downward direction, you will feel lighter. When the acceleration is in the upward direction, you will feel heavier. All right, so no acceleration, no change in weight. Acceleration is downward, you'll feel lighter. Acceleration is upward, you'll feel heavier. All right, so those are the facts that we were able to get. We were able to come up with. So let's do a quick review. Weight is the force of gravity acting on it, the measure of force of gravity. So it's going to be your mass times the acceleration due to gravity, which is roughly about 10. Your weight is going to differ from your mass. How? Mass is your measure of inertia, and weight is the force of gravity acting on it. All right, so what's a normal force? It's a reaction force to any force applied to a surface. It's going to be in the opposite direction of your weight. That's also known as the apparent weight if it's a scale reading. So if you're getting this reading from a scale, it's going to be your apparent weight. So is it possible for your apparent weight to be different from your actual weight? The answer to that question is absolutely yes. It depends on what you do on top of a scale. Also, it's going to be sensitive to your acceleration. So the reading that you get from a scale is going to be sensitive to your acceleration. So when the elevator starts to move from resting to downward direction, you will feel lighter. When the elevator starts to accelerate in the upward direction, you will feel heavier. And when the elevator is moving at constant speed, you will feel the same. Lastly, when the elevator starts to slow down to a stop while moving in the downward direction, you will feel heavier. All right, so the question becomes why. All right, so a little bit of math. Not that we will do any math, just there's a conceptual exercise that we'll do based on this. All right, so this is you inside the elevator. That's your center of mass. Located right here. That's your center of balance. You got weight, so that's the pull of gravity. Scale is located right there. You're standing on top of the scale, so there's a normal force. All right, so this is the scale reading. So N is the apparent weight, W is your actual weight. Elevator could be accelerating up or down or no acceleration. If it's accelerating up, that's positive. If it's accelerating down, acceleration is negative. All right, so we'll sum up the force along the y direction. N is up, positive, W is down, same negative. And this net force is responsible for the acceleration, up or down, along the y direction. Let's isolate N from here. So N is your scale rating, right? Scale rating is the apparent weight. N is your scale rating, so that's your apparent weight. So, all right, so add W to both sides. So I'm isolating N on the left-hand side. So N is about the reading that you get from a scale. W is your actual weight. So if the acceleration is up, mass times your acceleration of your mass is going to be added to your weight, so you will weigh more. If the acceleration is down, acceleration of your mass is going to get subtracted from your weight. As a result, you will weigh less. As a result, you will weigh less. All right, so that's what we have. So you can draw 3 conclusions out of this mathematical modeling. If the acceleration is up, so acceleration of your mass is going to add it to your weight, so you will weigh more. If the acceleration is down, acceleration of your mass is going to get subtracted from your mass. It's going to get subtracted from your weight, so which means that you will weigh less. If there's no acceleration, A is going to be 0. So scale rating is going to be the same as your actual weight. That's it. Okay, so we came up with a model that's going to agree with our observations. All right, so here's a bit of a mind twister. So I'm going to give you mind twister first. And then for those of you guys who get it right, I'm going to give you 20 points. All right, so this is regarding the person inside a falling elevator. Cable snaps. Imagine that this person is standing on a scale. At the moment the cable snaps, what is the scale rating? Okay, so how much will this person weigh according to the scale? Okay, so what do you guys think? So we got a person inside a falling elevator. All right, and the person is standing on a scale. So at the moment the cable snaps, how much does the person appear to weigh according to the scale? And why? All right, at this point you can either say something or put it in the chat, it doesn't matter.
I think it would weigh less because it says going down, right? If it's going down, it would.
Okay, so yeah, I heard you. So okay, what else do you guys have? Okay, so when the elevator starts to go down, when the elevator is accelerating in the down direction, you will feel less, right? I think you guys got that. All right, that's worth only 5 points so far. So the question is, how much less? All right, so column, how much less? I mean, what's the exact number you would see on a scale? That's what I'm looking for.
I mean, if you're saying it would be.
Oh, okay, so finally I'm getting some answers. Okay.
I would say 0.
Okay, so those of you guys who are saying 0, why are you guys saying 0? That's awesome. Okay, so those of you guys who said 0, give yourselves 20 points. That's beautiful, you got it. All right, so you will feel weightless inside a falling elevator, right? Case in point, here's the reason why. There are a couple of reasons. Number one, I'm gonna come up with a reason for this one. Acceleration is down. Acceleration is down. All right, so N is gonna be less than your actual weight. So apparent weight is going to be less than your actual weight because acceleration of your mass is going to get subtracted. So that's the reason why those of you guys who said less, I gave you 5 points, which is correct. Your weight is mg, right? When the elevator goes in a free fall, though, A is the same as g, right? So now you got mg minus mg. So it's going to be 0. Okay, so now we did learn something. Forget the math. Obviously, I'm not interested, but conclusion is you will be in a free fall, so will the elevator, right? Okay, so elevator and you are falling at the same rate. So which means that you're standing on the scale, but you're not applying a force on the scale. You and the elevator are falling at the same rate. So you cannot feel the scale under your feet. That's what it means. So you will feel weightless in a falling elevator. Just remember that. You will feel weightless in a falling elevator. So N is going to be 0. If you could look down on the scale, the value is going to be 0. So scale is not going to register in weight. All right, now let's do a little bit of physics. So far we've done mathematical modeling. Okay, so when the elevator starts to move from rest in the downward direction, do you feel heavier or lighter? About the same. When the acceleration is down, you will feel lighter, right? Okay, so we got that. You will feel lighter when the elevator starts to accelerate in the downward direction. Okay, so the question is why? Obviously, acceleration of your mass gets subtracted from your weight. So the question is why? Why is that happening? Okay, so remember the unstrapped objects inside vehicles will always move in the opposite direction of the acceleration of the vehicle. Car accelerates forward, your body moves backward. Do you remember the reason why? The reason why that happens is because of your inertia, right? Because your body wants to maintain its initial motion. When you apply a force on it, it's going to resist that applied force. All right, so you get that resistance to change the motion from your mass. So when the elevator accelerates in the downward direction, your body is going to resist that force. The resistance is going to appear as the deficiency in your weight. So that's what's happening. So you end up, in essence, you're measuring your inertia here. It's the tendency to retain the shape. Here, there's no change in weight. The reason is because your body is maintaining its initial motion. All right, so elevator is not accelerating, so you're moving with the elevator at the same speed. All right, so pick out the best answer. All right, so what do we have? We got a 175-pound person when the elevator is ascending at 2 meters per second squared. So the elevator is accelerating in the upward direction. Right? So when the acceleration is in the upward direction, you will appear to weigh more, right? So it's is the best answer. All right, so pick out the best answer for this one. I'm coming into the view. All right, so what do we have? We got an elevator that's moving upward. While it's moving at constant speed, the person inside weighs 600 meters, right? So that's the actual weight of this person. And it's moving upward, and then now if it's slowing down, do you feel heavier, lighter, about the same? All right, so I'm thinking that registers a value that's going to be less than 600 newtons during the time when the elevator slows down as it comes to a stop. All right, so this thing is moving in the opposite direction and slowing down. If it's moving in the opposite direction and slowing down, you will feel lighter. Because remember, your body is trying to maintain its initial motion as the elevator is slowing down, right? So your body is going to resist that change of motion, which means that you will feel lighter, if that's the case. So C is the best answer. C is the best answer for that one. All right, so 21, when the elevator starts to move from rest in the downward direction, you will feel lighter because, now you have to answer it, you will feel lighter because of inertia. All right, when the elevator starts to move, yeah, because your body is going to resist change of motion. It's just because it starts to move from rest in the downward direction, which means that it's accelerating in the downward direction, and then which means that your body is not going to want to, the body is going to resist that change of motion. Okay, so when the elevator starts to move from rest in the upward direction, you will feel heavier because your body, because it's got mass, right? So it's going to offer resistance to change of motion. All right, so that resistance is going to appear as the actual weight. When the elevator is moving at a constant speed, do you feel heavier, lighter, about the same? So you will feel about the same because once again, your body is going to offer resistance to change of motion, but then again, there's no change of motion here, so that's inertia. So the definition of inertia. So object at rest will remain at rest. The object in motion is going to remain in motion. So your body is going to keep on moving at a constant speed with the elevator. When the elevator starts to slow down to a stop while moving in the downward direction, do you feel heavier, lighter, about the same? You will feel heavier because your body wants to maintain its initial motion, so it's going to offer resistance to change of motion. And that resistance is going to appear as the extra weight on the scale.